Good morning and hello everyone. So I ended up in a different spot in each of the hours last time we met. So I'm going to back up a minute and pick everybody up in the same spot. So in this video, we're going to be talking about conservation of energy in more detail. And from this point forward, we are going to also limit our discussion to only kinetic and potential energy. So I'm going to start by drawing a picture where this picture is supposed to be the entire universe. And now I'm only going to be talking about the potential and the kinetic energy in the entire universe. If I added these two things up, that would be equal to the total energy in the entire universe. The problem is there's no way for me to know what the total kinetic and potential energy is. So even though we can't find the number, we do know that it always remains the same. But what we can do is we can look at smaller versions of the universe. And a smaller version, I sometimes call it a mini universe, or it's called a system in physics. And my mini universe or my system is going to, in this example, consist of only a cliff with a bowling ball sitting on top of it. Now, I'm not really sure how the bowling ball got on top of the cliff because at the start of the story, I'm sure the bowling ball was at the ground, and so I'm going to make the ground h equals 0. So we should always identify the ground in our system or mini universe. But somebody or something did work to get that bowling ball to the top of the cliff. So in my example, a physics student is going to do the work by lifting the bowling ball to the top of the cliff, but it could have been done by the Big Bang itself. It could have been done by a supreme being. I don't know how it got there, but we know that on our Earth, we have big boulders sitting on top of cliffs sometimes. All right, so the first thing I have to do is I want to calculate the work that the physics student did. So he placed a 7.26 kilogram bowling ball on top of the cliff, and the cliff is 122.5 meters high. So he lifted a bowling ball that has this weight, this high. So that's going to be, FW would be mg, so 7.26 times 9.8. And he lifted it 122.5 meters high. And that equals 8715.63 joules. So if this is how much work he did, that becomes the ET or the total energy of this mini universe. So I now know that this mini universe now has 8715.63 joules of energy. And the energy can always be shifting in its terms of its forms, but it's always going to be conserved. So the work will become the ET of the energy. All right, so the next thing I want to do is collect a little bit of data to see exactly what's happening in this mini universe. Because what's going to happen now is we're going to give that little bowling ball a nudge and it's going to fall straight down off the cliff. So at the start of the story, the distance fallen, it hasn't fallen yet, it's still sitting on the cliff. But if I wanted to calculate the distance fallen, I can find that from d equals 1/2 at squared. D equals 1/2 at squared. So I'm going to switch to Excel because I think we can fill in the chart a little bit more quickly if we do that. So over here, it has not fallen yet. But after 1 second, that would be equal to the distance fallen, d equals, would be 1/2, it's 0.5, times 9.8, 1/2 at squared times t, and then I'm going to square that. So it would fall 4.9 meters after 1 second. And you can see that I used d equals 1/2 at squared for each of those calculations. And because the cliff is 122.5 meters tall, it hits the ground after a perfect 5 seconds. Now the velocity, It has zero velocity at the start of the story, but we know that when something falls, it goes 9.8 meters per second faster every second. So after 1 second, it would be going 9.8. And I really got that number by saying that that is equal to 9.8 times the time that it fell. So 9.8. And then 9.8 times 2, 9.8 times 3, et cetera, et cetera. So it's going 49 meters per second at the end of the story. The height means measured from the ground. So at the start of the story, it's 122.5 meters tall. So what would its height be after 1 second? Well, that would be equal to the 122.5 minus how much it fell. And so we can take those numbers. Whoops, something's wrong there. All right, so this is equal to, you know what, I just need to change this to 122.5. All right, let me try that again. All right, that looks good. Okay, the potential energy. Potential energy is equal to mgh. So that's going to be equal to the mass, which is 7.26, times g, which is 9.8, times the height, which is this column. And so we can see our potential energy. And the kinetic energy is equal to 1/2 times the mass, 7.26, times v squared. So that'd be the velocity squared. So we can see that at time 0, all of the joules are in potential energy, and I don't have any kinetic energy joules. But as the bowling ball falls, my potential energy decreases and my kinetic energy increases. And at the end of the story, when it's on the ground and H is 0, I don't have any potential, and all of my joules have become kinetic. And the ET is going to always be equal to the potential plus the kinetic joules. And the ET should remain constant during the entire trip. And again, the ET equals the work that was done. All right, I want to do one other thing, is I'm going to insert a column here. Let's see if I can figure out how to do that real quick. Insert a column. And I'm just going to copy these times over here, because I want to see how these numbers change over time. So we're going to do a quick graph right there. So we're going to insert a chart. Let's do a scatter plot. And so let's look at that. So here are the times, and the potential energy starts big, so that's the blue dots. And so we can see the potential energy is decreasing. I'll say the word parabolically. It's not a linear decrease, it's parabolic. And the kinetic energy is increasing parabolically. And the ET is staying the same. Let me just try to pick a different graph here real quick. Insert and see if I can get one that connects the lines. It might be a little bit easier to see right there. All right, so the question then is, when is the kinetic and potential energy, when are the kinetic and potential energies equal to one another? So many people think that while it's fallen for 5 seconds, that it would be half of the time. But half of the time is 2.5. My graph needs to be slid over a little bit. It looks like it's starting at 1 and not starting at 0. But at 2.5, they are definitely not equal to each other. And what happens is they become equal to each other at half of the height. So whatever half of 122.5 is, that would give me half the potential energy. And if it's not potential energy joules, it would become kinetic energy joules. So let's go back then. And I want to quickly sketch that graph out that we just made. So if I graphed the potential energy, it starts big and it gets small. If I wanted to graph the kinetic energy, it starts at 0 and it gets bigger, and the ET remained the same going all the way across. All right, at the very bottom here, there's another set of graphs, and we're not going to make a career out of this, but these are called energy bar graphs, and I think you should just be familiar with what they look like. So we are going to do a graph for each of the seconds. So you can see that we have 0 through 5, so we have 6. 1, 2, 3, 4, 5, 6. So this is time 0. This is time of 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And we are going to put the ET in the first bar. We'll put the potential in the second bar and the kinetic in the last bar. And we can repeat those all the way across. So we know our ET is 87,000 or 8,700. So we could go up by, let's say, 1,000. So 1,000, 2,000, 3, 4, 5, 6, 7, 8. So that kind of works. So 1,000, so we'll call this one 2,000. We'll call this one 4,000, 6,000, and 8,000. So at the start of the story, the ET is 8715, so that would be, this is 9,000, so kind of like up to here. And this bar would be that tall. So this is how many joules of energy that we have. That ET bar is going to be the same in all of these graphs. But at a time of 0, all of the potential, or all of the joules were in potential. So I'm going to do my potential in blue. They were all potential. And I did not have any kinetic energy joules. So I'm going to put a little line down there, 0. But after 1 second, I got to look back at my Excel. After 1 second, the potential energy is approximately 8,400. So it's a little bit less, And my kinetic energy is about 350. So that would be like down here. But if I took this little piece and put it there, it would equal the red bar. I'll jump ahead and I'll do 4 seconds now is my last example. So again, the ET is going to be 8,700. And the potential energy at 4 seconds is going to be 3137. So 1,000, 2,000, 331, about right in here. And my kinetic energy is 5,056. So 1, 2, 3, 4, 5, about right in here. And again, if I added this bar and this bar together, it would be the same height as this bar, showing that my total energy is always the same, but it's sometimes in potential energy joules and it's sometimes in kinetic energy joules. All right, I'm going to stop this video here before we go on to the next part.